Good afternoon, everyone. My name is Suraj, and today we're going to be walking through discussion 11 from the fall 2019 iteration of Data 100. So in this discussion, the first couple questions are about gradients, gradient descent, and convexity, all of which are intrinsically related ideas. Then we will take a look at logistic regression and work through some calculations involving computing cross-entropy loss and probabilities. Okay, so let's get into it. In the first question, we're given the 3D plot of this multivariate function. Okay, so on the left, we have a plot of this function which takes in x and y and outputs x minus 1 quantity squared plus y minus 3 quantity squared. Okay, on the right, we have a plot of this function's gradient field. Okay, and what exactly a gradient field is that each of these points, right? So for example, at 2 comma 5, the vector that's at 2 comma 5 is the gradient of the function evaluated at 2 comma 5. And so as a refresher, what's a gradient? Well, it's essentially the multivariate equivalent of the derivative of a function, right? If you have a single variable function, the derivative of a function at that point tells you the slope of the tangent line at that point. So how much the function is increasing instantaneously at that point. The gradient sort of does that, but extended to multiple variables. Okay, so the gradient of this function will be a vector, and we actually compute it in part B, of two partial derivatives, right? In this case, our function takes in x and y as inputs. So we'll have a partial derivative with respect to x and a partial derivative with respect to y, both of which will tell us how much this function is increasing in the x and y directions instantaneously at that point. So it's really just a collection of partial derivatives, and we create a vector out of those partial derivatives, and sort of the direction in which the gradient is pointing tells you the direction in which the function is increasing at that point. Okay, so part A of this question tells us, from this visualization, what do you think is the minimum value of the function, and where does it occur? Well, so you can see that this function kind of looks like a bowl, and the gradient, right, and you can see that the value of this bowl is probably somewhere in there. You can see in the gradient field, as we get further and further away from the center of this plot, which is at x is 1, y is 3, the gradient vectors get longer and longer, which mean our function, roughly speaking, is increasing more and more quickly as we get further and further away from 1 comma 3. So our guess, just based off of that, should be that the minimum is at 1 comma 3. Okay, and what we can actually do is take a look at the function itself, x minus 1 quantity squared plus y minus 3 quantity squared. We notice that this looks like one thing squared plus another thing squared. We know that if you're taking some real number and squaring it, the minimum value that thing takes on is 0. So the minimum value of this entire function has to be 0. And so the minimum is of 0. And the way we get our function to output 0 is if we put in a 1 for x and a 3 for y. Then you'd have 0 squared plus 0 squared, which is 0. So the minimum value of this function is at 1 comma 3. And the minimum value itself is 0. And we can sort of tell that from the gradient field, because the magnitude of the gradient is smallest at 1 comma 3. And this is an idea we will look at in part C. In part B, we're told to compute the gradient of our function. So just for the sake of clarity, let me write it again. The gradient of my function, as I mentioned, is just a vector of partial derivatives. So first, let's compute the partial derivative with respect to x, which I can do by treating all other variables as being constant. So the partial derivative of this thing, I should have written f of xy. The partial derivative of this thing with respect to x is just 2 times x minus 1. I treat the entire second term as its constant, and the partial derivative with respect to y is 2 times y minus 3 by the power rule, right? And I treat the first term as its constant because it is completely independent of the y. And so now putting these two things together, I can get the gradient is just 2 times x minus 1. That's the first element of the gradient vector, and the second element is 2 times y minus 3. Okay, in part C, we're told to figure out when the gradient is equal to 0, what are the values of x and y. One important thing to note is that the 0 that's here is not the scalar 0. Rather, you can see that it's boldface, meaning that we're talking about the 0 vector, i.e. a vector of all zeros. So what we're really saying here is that the gradient is equal to the 0 vector, meaning that each individual element, i.e. each partial derivative on its own, is equal to 0. Right? So this is equivalent to two conditions. One, that 2 times x minus 1 is 0, which of course occurs at x is 1. And the other, when 2 times y minus 3 is equal to 0, which of course occurs at y is 3. So we're told that when the gradient is 0, we're not told, we figured it out, that x is equal to 1 and y is equal to 3, which is precisely where the minimum of this function occurs. Why were we looking at when the gradient was 1? Well, it's because that's what we've been doing in single variable calculus, right? In order to minimize a function, we would take the derivative of it, with respect to the variables we're trying to minimize, set that equal to 0, and then solve for an expression for our variable, right? And I mean, technically, we would have to do some sort of second derivative test, and in the context of gradients, we'd have to look at what's known as the Hessian, but that's sort of outside of the scope of this course. All you need to know for now is that we're looking at our gradient being equal to 0 because that's the multivariate equivalent of taking a derivative and setting it equal to 0. And you can see that when the gradient is 0, our function is minimized in this case. Okay? Not always, but in this case. And that's something we will look at in question 3. So the second question deals with gradient descent. And before we get into the nitty-gritty of this problem, I think it's important to talk about what exactly it is gradient descent does. So gradient descent is a numerical technique that tries to find the minimizing value of some function. Okay, so essentially what we're doing with gradient descent is implementing our own version of scipy.optimize.minimize, where we pass in a function and it gives us back the optimal value of that function, i.e. the value of the input, such that when I evaluate my function at that input, it's as small as possible. Okay, so it minimizes our function. And specifically in our case, what we want to do is minimize some empirical risk. Okay, and so we're trying to find the value of beta that minimizes our empirical risk, and we use gradient descent to do that. Okay, so it's an iterative algorithm, and what I mean by that is that at each time step, I improve upon my previous guess for beta. So we start off with some initial guess for beta, and it doesn't really have to be that well informed. And then from there, we iteratively improve on our guess for beta until we reach one of two stopping conditions. And I'll talk about those just in a second after I write down the expression for the update equation. And so, firstly, what does this cryptic looking thing mean? Well, it's saying my guess for beta at time step t plus 1, and that's what the parentheses t plus 1 means, is my guess for beta at time step t minus alpha, which I call the learning rate, or here we're calling the step size, it's really the same thing, times the gradient of the function I'm trying to minimize with respect to beta evaluated at my previous guess for beta. Okay, so this rule tells me how to update my guess for beta. I take my previous guess, subtract off some learning rate, which can either be constant or change as we do more and more iterations, and that's something you will have experience with in homework 7. That learning rate times the gradient of the function I'm trying to minimize. Okay, and here I'm trying to minimize this function called L, which has parameters beta, x, and y. And in this case, really, x and y are constants. They're the input-output pairs that we've collected from data. They're our observations. Beta is really the only thing that's changing here. Okay? And, we're saying we're trying to minimize our empirical risk, i.e. this function L. This really should, it says loss function, but it really should say empirical risk. But really what we're trying to do is figure out a value of beta where the gradient of our risk is equal to 0. Okay? And, we just talked about that idea in question 1. When we want to minimize a function, we're trying to look for when the gradient is equal to 0. And so that's exactly what gradient descent does. We keep improving upon these iterations as our gradient, and we hope that our gradient gets closer and closer to 0. And we know to stop when either A, the value of our gradient for our current guess of beta is sufficiently close to zero, right? And since we're dealing with, floating point errors and that sort of thing, it rarely will ever be exactly equal to zero. So we'll say if the gradient at our current guess for beta is sufficiently close to zero, like 0.0001 or something, we'll say we found the optimal beta, or we'll specify a maximum number of iterations. So we'll say, okay, let's update upon beta, 10,000 times. And if at that point our gradient is no longer decreasing, then we'll just stop and call it a day. But you'd hope to be in the first case where the value of the gradient at your current guess is close enough to zero that you know that you've likely minimized your function. And again, in question 3, we will look at cases when the gradient being equal to zero doesn't necessarily mean you've minimized your function, but let's assume that right now having a gradient of zero and minimizing your function are the same thing. So this is the update equation for gradient descent. And now our goal is sort of to just use this empirical risk function and sort of plug it in to this update equation for beta. Okay. The expression that I've written here is for a general beta, which typically will be a vector, right? We'll typically have beta be this vector with p elements in it. However, the empirical risk that we have here in it, beta is really just a scalar. So instead of taking the gradient with respect to beta, so instead of taking some sort of vector gradient, all I really need to do is take the partial derivative with respect to beta of my empirical risk, okay? And so the first thing I will do is do exactly that. I want to take the partial derivative of my empirical risk with respect to beta. And so this over here is a sum, and as a result, my partial derivative will also be a sum, right? Because the derivative of a sum is a sum of derivatives. And so now I need to take the derivative with respect to beta of this thing inside. The derivative of beta squared xi squared with respect to beta is just 2 beta xi squared. And the derivative of negative log of yi with respect to beta is 0, nothing, right? Because it's completely independent of beta. So this is what the derivative of my empirical risk looks like. And I can actually pull out the 2 and the beta out of this sum because they're completely independent of I, which is my summation index. So I can write this as 2 beta over n times a sum of I going from 1 to n of xi squared. And so what I've just computed now is this piece at the very end, the gradient of my loss with respect to beta. In this case, it's a partial derivative because beta is just a scalar as opposed to a vector. Okay, now all I need to do is plug this into the update equation that we've seen. So my guess for beta at time step t plus 1 is my guess for beta at time step t minus alpha, my learning rate or step size, times 2 beta over n, sum of xi squared going from 1 to n. And this should be beta at time step t because on each iteration we're evaluating our gradient or partial derivative of our function at beta from the previous time step, right? So in order to compute the update for beta at time step t plus 1, I use beta from the previous iteration, so time step t. So this right here is the update equation for beta in this specific instance, so for this specific empirical risk. Okay, and so that's question 2. So now in question 3, we're dealing with this idea of convexity. And so why is convexity important? Well, let's look at a little motivating example. Okay, consider this function here. So far in questions 1 and 2, we've sort of been operating under the assumption that if my function's gradient is equal to 0, I've minimized that function. Well, here, that is just not true, right? There are actually 3 points on this function where the derivative or gradient is equal to 0, but only one of them occurs at a global minimum, right? So here, the circled point is where the global minimum of my function occurs, but in these 2 other places, the gradient or derivative is also equal to 0. And we don't really need to look at this peak over here because we're only looking at minimums of some sort, so local minimums or global minimums, right? We wouldn't really consider this because it's not a minimum of any sort, it's a maximum. right? So this function has two local minimums, but only one global minimum. And so if we were operating under the assumption that we were in previous questions, we actually might find this left circled point to be the minimum, global minimum of our function, when it in fact is not, right? And so the danger with using algorithms like gradient descent on a function like this is that, suppose we start our iteration somewhere over here, we'll traverse in the opposite direction of the gradient, and we'll end up at this local minimum here. Since the gradient is equal to 0, we'll stop, call it a day, and say we've minimized our function, when in fact we haven't, right? And so over here is the global minimum, and this is the one we want to find. So on this function, depending on your initial guess, you may or may not actually correctly minimize your function. And so a convex function is just a type of function where all local minimums, I guess we should say any local minimum, is a global minimum. Okay? So a convex function is one where if the gradient is equal to 0, I know I'm at a point where my function is minimized not just locally, but globally. Okay? And so that is, as I mentioned, not true of this function here. And there are three equivalent definitions that we can look at for a function to be convex. So the first one is that walking in a straight line between points on the function keeps you above the function. Okay, so one way to visualize this is that if I pick 2 points on a function and I connect the dots, that line should be on or above the function. And this line is also called a secant line. Okay, so if I draw the secant line over here, clearly it's on or above the function. But that's not true of all secant lines I draw on this function, right? If I, for instance, pick this secant line, then this line is not on or above the function, right? It's below the function. So this function is not convex everywhere. It's convex in some places, but it's not globally convex, and that's what we mean when we're talking about convex functions. So we would say this function is not convex. Another condition, or an equivalent condition that is for a function to be convex, is that the tangent line at any point lies below the function globally, and the function needs to be differentiable for us to figure out a tangent line, right? Because the slope of the tangent line is the derivative or the gradient at that point. We won't really visualize that for our purposes, but you can see, for instance, perhaps at this point, the tangent line for the function over here is something like that, and it's above the function, right? And so that violates the second property. Right? I mean, if it violates any one of these properties, it'll violate all of them because they're all equivalent. And the third property is that the second derivative of this function is non-negative everywhere. So the second derivative is 0 or greater everywhere. And if you think back to, the first time you took a calculus course, if you took one, you saw that if the second derivative of a function is non-negative, that means the function is concave opening up. So it forms like a bowl type shape or something like that opening up. And so that if you have arrived at a local minimum, it'll actually be a global minimum. Okay, so those are equivalent conditions for convexity, but probably the most easy one to look at visually is the first one. Okay, and so in part A, we're asked, is the function described in question 1 convex, and make a visual argument. So if we go over here, I feel like I've mentioned this a lot in this video, but this function looks like a bowl opening up. And if you were to connect, or pick 2 points on this function and draw that secant line, it would always be on or above the function. Right? You think about a bowl, pick 2 points on the bowl, connect the lines, or connect the dots, and that secant line will be on or above the function. So it's concave opening up everywhere, so this function is indeed convex. Okay, and there are ways to determine this algebraically as well with what's known as the Hessian matrix, but again, not in the scope of this course. In part B, we're asked to find a counterexample for the claim that the composition of 2 convex functions is also convex. Okay, and so let's define my 2 functions here. And there are many counterexamples you could use, but this is probably the most commonly used one out in the world, I guess. So let's say that f of x is x squared. Okay, clearly a convex function, if I pick any 2 points on this curve and connect the 2 points, that secant line will be on or above the function. Alternatively, you could compute the second derivative of this. You'd get that it's equal to 2, which is non-negative everywhere. It's constant everywhere, actually. And so that means, it satisfies the third property. Another function I will look at, g of x, is negative x, which looks something like this. Okay? This function, believe it or not, is also convex, right? Because the first property is that the secant line between any 2 points has to be on or above the function. And I just realized the worksheet doesn't say that exactly. This says above, but it should be on or above. Okay? If it's on the line or on the curve, that is okay. That satisfies the definition of convexity. There's a type of convexity called strong convexity in which you need to be strictly above the line, but that's not within the scope of our course. Convexity is satisfied even if the secant line is on the curve, okay, on or above. And so by that definition, g of x here is also convex. But what happens when I compose these 2 functions? Let's just say h of x is g of f of x. So it's the negative of x squared. Well, that looks like this. So it's a bowl opening downwards. And here, clearly, this function is not convex, right? If I pick 2 points on it, connect the 2 points, the secant line is not on or above the function. In this case, it's below. So negative x squared is not convex, but x squared and negative x on their own are convex. So it is not true that the composition of 2 convex functions is also convex. Okay, so hopefully that cleared up some ideas revolving around convexity and sort of showed you that if we use gradient descent on a convex function, we will almost always find the global minimum. But if we use gradient descent on a non-convex function, the minimum we find may not necessarily be a global minimum. It might instead be a local minimum, which is dangerous. So the last 2 problems on the worksheet are about logistic regression. Okay, as a quick refresher, with linear regression, our goal was to predict some sort of real valued quantitative output. So for instance, given someone's midterm 1 grade and midterm 2 grade, you wanted to predict their final exam grade, which could be any real number, probably greater than 0, but it could be any real number. Our goal now is to do some sort of classification. Okay, so instead of predicting some real valued output, we want to predict some qualitative categorical label. So for instance, instead of predicting, what their final exam grade is, we want to predict whether or not they'll pass the class, yes or no. And so the specific type of classification we'll focus on in Data 100 is binary classification, where we have 2 different classes, one of which we'll call 1 and the other will be 0. So we want to predict a 1 or 0 given a bunch of quantitative features. How we will do that is by logistic regression. Okay, and logistic regression doesn't output a 1 or 0, rather it outputs a probability, and specifically it outputs the probability that our observation x belongs to class 1. Okay, so our model for logistic regression is the probability that y is 1 and y is our class, given our observation x, and we say that that's equal to the sigmoid of x transpose beta hat, where x and beta hat are both vectors. And so, before our model, we really just took x transpose beta, right, where x was our observation, beta was our, weights vector, took the dot product of those 2 things, and we computed our output like that. Now, really, the only difference is we feed that through this sigmoid function, which has the nice property that all of its outputs are bounded between 0 and 1, so we can interpret them as probabilities. Okay, and the shape of this sigmoid curve is something like this. It's S-shaped, and that's not a great drawing. You might want to refer to the textbook or lecture slides for a better drawing of the sigma. Anyways, in question 4, we were told that given this scatter plot of data below, what we want to do is draw a reasonable approximation of the logistic regression probability estimates for the probability that y is 1 given x. And so we see that if x is really small, almost all of the y values are approximately equal to 0. So we know that our probability for belonging to class 1 when x is really small is probably going to be really low. Okay, maybe something slightly increasing like that. Similarly, when x is really high, almost all of the points belong to class y is 1. So our probability will be pretty high. And then in the middle is where all of our uncertainty is. And so that's where our probability will be, something closer to the middle. So something closer to 50%. And so we essentially just fit our sigmoid curve here, and it looks something like that. And again, that's not really that great of a sigmoid curve, but it'll do for the purposes of this video. In number 5, we're told that we have a classification data set consisting of two xy pairs, 1, 0, and negative 1, 1. So to be explicit, this is x1, y1, this is x2 and y2. Okay, the covariate vector x for each pair is a 2-element column vector 1 and x. So what this is really saying is, in order to come up with your, vector corresponding to a single feature, you take your scalar xi and put it in a vector along with the value 1. And the reason we do that is so that we can have an intercept or a bias term. Okay, we run an algorithm to fit a model for the probability that y is 1 given x, and this is what we just looked at before. And here's the formal definition of the sigmoid, 1 over 1 plus e to the minus t. And our algorithm returns some value for beta hat, negative 1/2 and negative 1/2. What we want to do in part A is calculate the probability that y is 1, given that x is this vector 1 and 0. And so, as outlined above, this probability is just the sigmoid of x transpose beta hat. Okay? In this case, x is 1 and 0, so x transpose is just this row vector, and beta hat is negative 1/2, negative 1/2. Okay? What I'm doing here is computing just the dot product of x and beta hat. And so this ends up being 1 times negative 1/2 plus 0 times negative 1/2, which is negative 1/2. Okay? Now I evaluate the sigmoid of negative 1/2, which is just 1 over 1 plus e to the minus 1/2. And so I have the double negative, so I can just replace this with the 1/2. And that is my probability that the observation 1, 0 belongs to class 1. And I mean, this is a probability that's kind of an unsatisfying answer because you don't get to see what it is between 0 and 1. It turns out that this is actually close to 0.38, at least that's what the solutions say. But I mean, if this were an exam or something, you could leave your answer as what's in the box, and rather you should leave your answer as what's in the box because that's an exact value. Okay, so given an x vector and a beta vector, all you need to do to compute the probability that y is 1 given x is take the dot product of x and beta and feed it through the sigmoid. In part B, we start talking about cross entropy loss, right? And so far in the course, we've primarily used L2 loss as our loss function. And I mean, when we were dealing with linear regression, L2 sort of formed the backbone of the normal equations and whatnot. And in lecture we talked about several reasons why using L2 loss for logistic regression wasn't a good idea. And there were several reasons. 1, it's not convex. 2, it doesn't penalize wrong predictions as much as log loss or cross entropy loss does. And 3, cross entropy loss has more direct relevance in comparing probability distributions, so it's more well suited for 0, 1 values than L2 losses, and that's sort of outside of the scope of this course. But typically with logistic regression, we use cross entropy loss, which is defined right here. And notice the minus sign out here. So really this should say minus yi log yi hat minus 1 minus yi log, let's move this over here perhaps, 1 minus yi hat, where yi hat is just the probability that y is 1 given x, and so 1 minus that is the probability that y is 0 given x. Okay, this is perhaps just a slightly cleaner way of looking at the same expression. Okay, in the preamble for part B, it sort of cleans up the expression for cross entropy loss, and then it gives us this function r of beta, which is our empirical risk, which of course is the average of our cross-entropy loss over our entire data set. Okay, in part B, what it wants us to do is write out the empirical risk for the data set 1, 0 and negative 1, 1 as a function of beta naught and beta 1. Okay, so one thing to note is that here we need to calculate two separate cross-entropy losses and then take the average of those two things. Okay, so let's start first with the data set 1, 0. Okay, here it's important to mention that our vector x is actually the vector 1 and 1, right, by this definition over here, right, where we take 1 and then our scalar value of x. And our value of y is 0. Okay? And so now when it comes to actually computing the cross-entropy loss for this point, what we will do is use this expression that's down here. But if you're computing the loss for just a single point, I personally think it's a little more straightforward to look at this expression because you know your true y value is either 1 or 0. If your true y value is 1, this entire second term becomes 0 because 1 minus yi then is just 0. If instead your actual y value is 0, then this first term is 0 because yi that you're multiplying by is 0. Okay, but just to stay consistent with the solutions, we will use this expression that is down here. So the cross-entropy loss for this point will be negative, and then the negative is coming from here. I want yi xi transpose beta. And so that's yi, which is 0. And so I actually don't even need to compute this first term, right? Because this over here is equal to 0 since my yi is 0. So all I need now is the log of the sigmoid of negative xi transpose beta. So negative 1, 1 dot product beta naught beta 1. And so now I just need to simplify this. So I have negative log of sigmoid of negative. What's the dot product of this vector with this vector? Well, it's beta naught plus beta 1. Right? And so I can write this as negative beta naught plus beta 1. Okay, so that's the loss for our first point. Our loss for our second point now, it'll be a little more complicated because yi is actually equal to 1. So this first term we actually need to look at. But that's not an issue. We are looking at negative 1, 1. So our x vector is then 1 and negative 1, again by the definition that's up here. Right? I just plug in my scalar negative 1 down here, and that gives me my x vector. And y2 is equal to 1. So the cross-entropy loss for this point is negative 1 times the dot product of x and beta, which in this case is beta naught minus beta 1. Right, and the reason I got that was because, if I write beta over here, like beta naught, beta 1, beta naught gets multiplied by 1, beta 1 gets multiplied by negative 1, and so that's where this comes from. And then I have plus log of sigmoid of negative xi transpose beta. Well, if xi transpose beta is beta naught minus beta 1, the negative of that will just be beta 1 minus beta 0. So this is the cross-entropy loss for the second observation. And then now, in order to put this together for the two observations together, I just do 1/2 times this first quantity plus this second quantity. Okay, and I guess I'll write it out for the sake of completion, and the solutions simplify it in a very specific way, but I don't really think it's necessary to simplify it in the exact way that the solutions do. All that I think is necessary is that you're able to write out these expressions on their own. But again, just for the sake of completeness, I will combine these two things, and so let's say empirical risk is equal to negative 1/2, and I'm factoring out the minus sign now. I have log of sigmoid of negative beta naught plus beta 1 plus beta naught minus beta 1 plus log of sigmoid of beta 1 minus beta 0. Okay, so that's the empirical risk. What I have highlighted, actually, let's clean things up. This is the empirical risk. Okay, and if you work it out, you'll see that it's equivalent to the expression that's given in the solutions. But again, I don't think it's that important that you're able to work it out until this point. Okay, lastly, in part C, we're told to calculate the empirical risk for beta hat is equal to this vector for the same two observations. Essentially, what it wants us to do is plug in beta naught is equal to -1/2 and beta 1 is equal to -1/2 into this expression for empirical risk. And it turns out that this is actually not that difficult to do because beta naught and beta 1 in this case are equal, so this term and this term are both equal to 0. So let's compute it. Okay, and so remember, this over here is beta naught, this is beta 1, perhaps there should be hats on there. So I have -1/2 of log of sigmoid of negative. Now what's beta naught plus beta 1? Well, since they're both equal to -1/2, I sum them, I get -1. Since there's a minus sign here, those cancel out, and so now I have the log of sigmoid of 1. Okay, plus beta naught minus beta 1, well, both of those things are equal, and so their difference is 0, plus log of sigmoid of 0, right? Because beta 1 minus beta 0 is also 0. Okay, so this is what my empirical risk looks like, and just because it's not too difficult, let's actually simplify this out just so that you can see that it matches what the solutions have. Okay, so I can write this as -1/2. What is the log of sigma of 1? Well, that's just the log of 1 over 1 plus e to the -1. Okay, plus 0, which we can sort of drop, plus the log of 1 over 1 plus e to the 0. Great. Now we can use log rules, and specifically we'll use the fact that the log of a over b is equal to the log of a minus the log of b. Right? We will use this fact now. To do a little bit more simplification, we can write this as -1/2 times the log of 1 minus the log of 1 plus e to the -1. Okay? And then I'll apply that same rule here. Plus the log of 1 minus the log of, log of 2. Right? Because e to the 0 is just 1, so the denominator is 2. So my numerator is 1, denominator is 2. Now I can rewrite this yet again, -1/2. I can combine my two log 1s into 2, literally, times log of 1, right, because they're two terms that are equal, minus log of 1 plus e to the -1, minus log of 2. And I can actually combine these two terms again by multiplication. And so I can actually write this as -1/2, again, rewriting this term, 2 log of 1 minus the log of 2 plus 2 e to the -1. Okay? I just multiplied this 2 into this parentheses. Now, there's a simplifying step that I should have made earlier. It's the fact that the log of 1 is 0 for any base, right? Because what the log of 1 is saying is give me the exponent I put on my base to get 1. Well, any base raised to 0 is equal to 1, so the log of 1 is actually just 0. And so this simplifies to 0 minus the log of 2 plus 2 to the e to the -1. And so it actually, I dropped the 0. It turns out that these two minus signs cancel out with one another, and I can write this as 1/2 of log of 2 plus 2 to the e, 2 times e to the -1. Okay, and I realized that was a pretty long-winded derivation. Hopefully I didn't misspeak during any of those steps, but this expression matches exactly what you find at the end of the solutions, which hopefully tells us that what we did in part B was correct, even if it wasn't fully simplified. Okay, so just to quickly recap what we just did in problem 5, in A, we used a value of beta hat that was given to us in order to compute a probability. In B, we wrote out a general expression for empirical risk in terms of beta naught and beta 1. And in part 3, we were told, okay, assuming that we were given a value of beta hat, so similar to part A, compute the value of the empirical risk numerically for this given data set. And that's exactly what we did. So that wraps up the logistic regression portion of this worksheet, which means I think we are done with discussion 11. If you have any questions about this, feel free to post on Piazza. And if you're studying for an exam while watching this, good luck.